All right, can you see my screen?
Yes.
Today we'll be talking about network routing. Slightly a detour, but interesting problem. So what are we given? We are given a graph. You can call it a network, represented by set of vertices V and set of edges E. So let's call this. So SIs are going to be sources. And TIs are respective sinks where these sources want to send information. Other nodes are just V1, V2, V3, and so on. And there is some directed graph given to you. Let's just connect. All right. So now DIs are going to be demands for SI to TI pair that you want to route this much amount of, let's say, information from source SI to TI. All right. Now edges are not capacitated. You can put as much as you want on each edge, but we will count in some sense the load on each edge by defining particular functions. So as edges are not capacitated, but there is a latency function you can call it latency or cost function for each edge E, which we will define as LE. So LE is a function from amount of flow you're going to assign to particular edge E to R plus. All right. So far so good. We will make two modeling assumptions. One is unsplittable. So before that, I should define what. So now DI, so let's say D1 is the demand for source S1, which should end up at T1. All right. So the outflow from S1 should at least be D1. The inflow, in this particular case, it turns out T1 has only one edge. So at least this much amount of flow has to come in through T1. In this case, the inflow should be at least D2. There are two edges coming into T2. And similarly, there are three outgoing edges on S2. The total demand out has to be D2. And on any other vertex, which is not a source or destination, the net flow in and the net flow out should be equal to 0. The difference between the net flow in and net flow out should be 0. All right. So this is what we mean by demand being satisfied. Now the case is here, as you can see, S2 has three outgoing nodes. If you're allowed to use as many paths going from S2 to T2 to route the demand D2, we call it the splittable flow problem. However, if you require that only one path be used, that is called the unsplittable problem. All right. So distinction is clear what splittable and unsplittable mean. You can use more than one path in the splittable case, and you can use exactly one path to route the demand for the unsplittable case. So unsplittable case is slightly more difficult than the splittable case. As usual, on arrival of a request, which is a tuple, SI, TI, DI, a path or multiple or a single path has to be assigned for it. Multiple in the splittable flow problem, single in the unsplittable flow. Now let's look at a particular edge E and let the flow belonging to request K, which is nothing but SK, TK, DK, passing through edge E B. This is a notation which you should remember throughout the class today. So E is the edge which goes in the subscript, and K is the request, that is the demand DK between SK and TK. That's the kth index. So that goes in the superscript, edge goes in the subscript. All right. So my edge flow flow neutrality constraint should tell me that for any vertex which is not a source or a sink, the following condition should be satisfied. So for any V, so E belongs, so I'll just define what delta plus is. So for edge E, all the incoming edges are delta neg and all the outgoing edges are delta plus. So this is V1 and V2. So delta plus V2 is going to be all the outgoing edges from V2, and delta neg of V1 is all the incoming edges to V. So for each edge belonging to either this and this, essentially a node should have flow neutral for V which is not equal to any Si comma Ti. All right. Any questions so far? Please feel free to stop me. For us, yeah.
Yeah, sir, can you repeat once that splittability assumption?
So there's not assumption, it's a modeling thing that can you split the flow going from the source to the destination. So splitting means can you route your flow over multiple paths or you have to go over a single path. So if you can't go over multiple paths, it's called the unsplittable problem. If you can go over multiple paths, it's called a splittable problem. So it's not an assumption. We'll look at both these cases.
Okay.
Yeah. Now for a V, which is some for some I, or let's say some K, just F E K minus F E K, E belongs to delta plus V minus should be equal to, so dk has to be sent out from that particular node which is a source for sk, and similarly fek minus fek E belongs to delta neg of V should be equal to minus dk for V equal to dk. All right, so these are our flow balance equation. So source should send out a positive flow out, a sink should get a negative flow, like send out negative and get in positive flow, and for every other node in the network, the net flow should be 0. All right. So let some more notation. Script f ek be equal to fe1. So we are fixing a particular edge, but looking at all the demands up to 1 through k. Be the vector that represents the amount of flow passing through edge E for the first k request. First k. So you're fixing an edge E and looking at FE1 is the first request. It's also taking FE1, FE3 and so on. So that's what the full vector FEK means. The full vector, all the flows passing through an edge E. Now using this, we will define the cost of assigning an additional flow given what you've done in the past. So let FEK minus 1 be the current flow vector through edge E. So now assigning amount of flow FEK, how much cost do we have to incur? That's how we define the cost of. So CE of FEK given the current status is FEK minus 1 is equal to integral 0 to FEK LE, which is the function I defined early on, summation FEI, I going from 1 through K minus 1 plus Z dz. Can somebody interpret this for me? Where LE is some function defined for F2R. Can somebody interpret my cost function? Is it clear, first of all, what I'm trying to do? I'm defining the cost of assigning an additional flow given my current status, which is script FE K minus 1.
So like from the time k minus 1 to time k, I am increasing my flow by fe of k. So
No. I'm increasing the flow by incrementally
yeah.
Z. So that's my increase in. So this is the so if you fix a Z, this is the if I give a small amount of flow to it, this is my increase, and I'm integrating it over with respect to the total flow you're giving me. See, this function LE need not be linear. So that's why we're defining it this particular way. It could be something like a sublinear function, or what you, if you know what a submodular function means. So can somebody interpret why this is a reasonable way of doing this?
So like the cost incurred while increasing the flow infinitesimally, it might depend on the current flow in that
Okay.
edge.
So suppose your function is, let's say LE of x is x square. What does this mean? That you're already, let's say you're already high enough. So you're already, so this is, so remember, this is the sum of the flows currently passing through edge E already. And I'm adding additional Z. So suppose you're already at a level which is summation FEI, which is quite large. By doing this, for every Z, I'm asking you to pay a high additional cost. If I made it this linear, I would not care what is my current loading. So this is trying to load balance in some sense, that if the load is already high, I would not like to load additional amount of flow on the same edge as before. Make sense? Is everybody clear what my cost function is? So this is defined incrementally. You can define it directly also. So for like equation number 1 is defining it incrementally. First flow, second flow, third flow, fourth flow, and so on. But if you want, you can write it succinctly over all flows also by doing this addition. Everybody okay? So let's look at examples which are useful, or rather we will look at. So one simple is a constant function. Things will be easy. LEX, which is a linear form, AEX plus BE, which is what we look for most of the class, or it can be polynomial such as AI x to the power I. So this will be the one we'll actually worry about the most in the class. So the overall cost of an online algorithm A for the kth request is obtained by summing this equation number 1 over all edges through which flow is going through. So overall cost.
So what does that C indicate? Function C.
Give me
Yeah.
just the cost. Give me one second.
Yeah. Sure.
So CK is summation E belongs to all edges CE FEK FEK minus 1. Okay, now ask me. This is just a notation for cost.
Okay.
So the cost that the edge E incurs if you additionally assign a flow of FEK, given that currently the flow vector is script FE of K minus 1.
Okay.
So the cost of assigning the kth request with my algorithm is then simply this summed over all possible edges, and the overall cost is summed over all capital K requests. So a lot of notation. Capital K, little k, 1 through capital K, C. And our, as usual, mu k is max over sigma ck sigma over ck opt. All right. Let's look at an example after we've done all the work. Think about a network which is very small. 1, 2, 3, and 4. So now can you tell me input sequences for which any online algorithm will suffer? So input sequences means pairs Si, Ti, and Di. Guys, what happened? It's a very simple network. Is everybody online?
Yeah.
Okay.
Is this for constant cost or linear?
You can choose whatever you want. So LE is like, for the moment, you can leave it abstract. Just think about what the input can be for which every LE will struggle. Like, all we want to exploit is the fact that the offline algorithm knows all the requests in advance, while an online algorithm does it causally. That's all. You can choose LE. You can leave it LE abstract. No problem. It's just like obvious. So suppose 1, 4, 1. What does this mean? 1 unit of demand is asked from 1 through 4. So what will an online algorithm do? You can split, you need not split. It's up to you. So let's look at the splittable case. What will you do? There are only two paths. Correct? So either some of it goes through this one, let's say F1, and some of it goes through F2. Now, given that I have done this, what is my next input going to look like? So suppose A fulfills 1, 4, 1 via F1 through 1, 2, 4 and F2 1, 3, 4. Okay. So let me just make this. Now, given this, what should be my next input? So that F1 plus F2 is equal to 1.
So if F1 is larger than F2, then I'll give the next input as 1, 2, 1.
1, 2, 1. What if F2 is not larger? Suppose F1 is equal to F2. Online algorithm can do that, right? Will it matter what you're saying, or will it still hold?
Yeah, then also it will hold.
Okay, so now tell me. So it's 1, 2, 1, right? So this is not negotiable. I have to put a unit amount of flow on this one, right? So A has to put F3 is equal to 1 over 1 to 2. So what is the over edge 1 to 2? How much is the total flow now? 1 plus F1. And over 1 to 3 is simply F2. And what will OPT do on the same input? Just use edge 1, 3, 4 for 1, 4, 1 and edge 1 to 2 for 1, 2, 1. So irrespective, as long as LE is increasing in both cases, an online algorithm is going to struggle. Is this clear? That why this is worse than this?
Yes.
See, typically you should think of this in terms of convex function. So what does a convex function want? It wants to have, if you're minimizing the sum of convex functions, the minimizer is typically where everybody is given the equal weight. So if you, let's say, minimize summation f here f of xi from 1 to n summation xi equal to m, and let's say all fi is equal to fg. Doesn't matter. What do you think is optimizer for f convex where xi's are all equal? Do we know this fact? So that's exactly at play. So rather than giving 1 plus f1 or some non-symmetric flow, an OPT is able to give a unit flow on both of these edges and minimize its cost. That's precisely what is going on. So an online algorithm is always going to pay a penalty for even for this very small example, and for larger examples only larger. Are we okay with this example? Did everybody get what are we trying to do? We are trying to do in some sense load balancing, if you want to say it in that particular way. That we want to put an equal amount of flow on all paths, where equal is subject to the change in the latency function L sub E. So if one particular edge has very large latency, it will have proportionately less flow going through it. But if all LEs are the same, and if there are multiple paths, you would like to load all these paths equally. Now the causal information-ness of it is going to come in your way. If you knew everything, you would just solve a convex program and get over it. Here, because you're only going to get revealed this information sequentially, you will make mistakes. So you want to see what algorithm will not make too many of these mistakes. Is everybody clear with the trade-off? What are we fighting against?
Yes.
All right. So now, candidates, algorithms. So anything which comes to mind, what we should do? So what is the information available on the kth request arrival? What have you done in the past? You already assigned these requests. You are not allowed to change those requests. All you can do is, given that, you can choose what you want to do now without knowing what's happening in future. That's it. Think of the most natural thing. What will you do? If you're posed this problem and you're sitting at the kth request arrival, you already know what you have done in the past. What would you like to do?
Kind of split it equally.
That's complicated, right? Splitting equally because each of these functions L sub E are potentially different. And also your previous allocations are also could be unequal. Right? So so essentially what you're saying is look at all the paths from Sk to Tk and equalize the flow or equally divide dk among all these paths. That is not a good idea, right? Because of two reasons. One, the latency functions L sub E are different, and what you've done in the past could be very different on different paths.
So the shortest, I mean, where the flow is minimized, there I'll add the flow.
So this is Sk and this is Tk. This is your network in between, which already has lots of flows assigned, okay? So these are your connections to the network and these are your, so and each edge here, currently what, so I know LE and summation FE L, so not L, FEI, I going from 1 through K minus 1. This is what I know currently. For each edge, I know the latency function and the current amount of flow going through it. And I have this new demand dk. Now tell me what you want to do.
So I can think this as a weight of the edges, and then find the shortest path from Sk to T can actually
But
add.
that is in some sense an unsplittable problem. You're allowed to split right now. So in the unsplittable case, I can understand what you're trying to do. Because you have to find a single path, so you'll find the one path which minimizes the cost. So that's okay. Given my current allocation. In the splittable case, what should I do? Always remember, algorithm complexity is not my problem.
Optimize locally, like given what the current state of the network is, find find a flow that that will incur the minimum cost.
Right. So I defined something for you, right, before. So I defined the overall cost of an online algorithm for the kth request. So are you saying find a flow which minimizes C little k?
Yeah.
See, this is already frozen. I can't touch this. All I can do is I can look at the local cost and I can try and minimize my local cost. Do people find this reasonable? I'm not telling you how to do it. I'm saying somebody does it for you. Does it make sense? It's like greedy in some sense. But given where you come from, at this point onwards, you think that your prior decisions were correct, and given that those were correct, you just make the right decision at this point. So it's a local algorithm. The negative result is, the first negative result to begin with is that lemma for, this is also true for the unsplittable, for the splittable flow route or network routing problem for general latency functions L sub E, the competitive ratio mu A is arbitrarily large for any. So if any's are arbitrary, only satisfying properties like they're non-decreasing, you can't hope to do, you can't hope to find an algorithm which is reasonable. And it's not very difficult to show this. We'll actually show this in the homework. So for this reason, we will limit ourselves, at least for today's class, to the class of linear latency functions. which is LE will be AEX plus BE, where AE and BE are going to be greater than or equal to 0, but arbitrary. So there is no dependence across different edges. A and B could be arbitrary across different edges. All right. Now for this case, can somebody, so now we look at this greedy algorithm A, which minimizes the cost CK over FEK, which is given by CE FEK given FEK minus 1, summed over all E belonging. Okay, now for this type of functions where LE is equal to AEX plus BE, what do you think? Can I efficiently solve this problem? So let me ask you in a different way. Is this problem convex?
Yeah, I think so.
It's convex, and why is that?
When you integrate LE, you get something like X square.
Right. So what was CE? Just to recall, what was our CE of FEK minus 1? Does anybody remember? This was the form, right? So now given that LE is linear, what do I get? I get AE times so what do I get? So I get simply AE I going from 1 through K minus 1 FEI times FEK plus AE times FEK whole square by 2 plus BEFK. I'm writing out because we'll use this over and over and over. Okay. So now, whatever you want to say, what are the decision variables here? When I put it back into this. So decision variable is FEK. And in what form do they appear here? FEK appear first as a linear term. So not fine.
Quadratic, right?
Right. So that is why this is actually a convex program. And I can not only efficiently solve it, but use some of its properties. So what is the most important property of a convex program at optimality, which you might be aware of? The optimal solution has to satisfy something. We know that at optimality, the derivative is 0. It's a convex program. So if I can find a point where derivative is 0, I am good. What more do we know? Heard of the KKT conditions? Anyone? Everyone?
The gradient would be a linear combination of the gradient of the constraints.
What is the gradients of the constant? So if you've not seen KKT conditions, I request you to look at the simplest, even Wikipedia page is fine. Look at the convex programs and see what KKT conditions mean. The implication of this for our program will be the following, which are not difficult to see. So I'm writing in compact form. LE is of course AEX plus BE. 3K. Where FEK solves my convex program, while XEK is any other flow. Can anybody interpret this, why this should be true? And moreover, you can also try to see. I will define what P and Qs are in a minute. Where P is any path used by CP, convex program, to assign non-zero flow, while Q is any other path. From SK to TK. Let's call them 2 and 3. Can anybody like interpret how to get there? It's okay, but can at least somebody argue that this better be true? If FEK is optimal for solving CP, should 2 and 3 be true? So what is this part? Just this part of the function. This is the latency after assigning the newer portion, which is FEIK or FEK, sorry.
Yeah.
So now you understand what it means, that I'm adding over all possible edges the function after multiplying with FEK. Now what does that mean? Is the question clear? We're just trying to interpret why 2 and 3 should be true. Where hopefully the symbols are clear. FEK is the flow which your convex program gave you, and XEK is any other flow for the care demand. Okay, if 2 is difficult, somebody wants to try 3. What is 3 telling you? That look at any path P which is carrying non-zero flow from SK to TK. And E belongs to P. I'm only adding all those edges which belong to path P. Why should 3 be true? And Q is any other path from SK to TK. So let's say this is P. Q might have some overlap. Okay, Q. It's not that Q is completely disjoint. Now P is a path over which non-zero flow is assigned by my convex program or the greedy algorithm. And Q is any other path. What property do you think should be true? Just by the definition of P.
Yeah, like the total loss over P must be lesser than the total loss over Q. Otherwise, it would be suboptimal.
No, you can switch, right? If it was not the case, then Q should be the path. And
Yeah.
that will give you a contradiction. So 3 is kind of easy. Now let's come back to 2. And just look at the way the cost function is defined. Is my writing clear, right? That what we are asking?
Okay. So it is a linear part of the cost function. That is that is AE times the flow up to K minus 1 plus BE times FE to K. So that is what LE of the summation up to K FE of I times FE of K.
Okay, you want me to expand? I'll expand. So LE of summation I going from 1 through K FEI is nothing but AE summation I going from 1 through K FEI plus B. Okay, that's what does this. So now we are saying we multiply this with FEK, and here you multiply with XEK, which is some other flow. The left hand side should be smaller than the right hand side.
Actually, before adding some additional flow, so this was the cost, right? LE
No,
summation.
no, I'm adding it's K already included. Okay.
Oh, okay.
So which part of the cost are we counting? Okay, this is a good exercise. This will make sure that you read KKT condition and argue this. All right. The third is 3 is clear. Just make sure that, but we'll keep using 2 repeatedly because that's our hook compared to what essentially we'll do is XK could be any flow, including what OPT can do. So that's what we'll try to hook our algorithm with respect to. All right. Any questions at this point? Other than proving 2? Is the algorithm clear, right? Algorithm is clear to everybody. We're just trying to solve a convex program, which is a greedy optimization. So theorem, the greedy algorithm for affine cost function, affine latency function, L equal to X plus BE has a competitive ratio of at most 4 capital K square over 1 plus K whole square, where K is the capital K is the total number of requests. So letting K large, essentially it is how much? 4. All right. Now the proof is actually elementary. Lots of inequalities. So stay with me. Okay. So recall C, or let me just F E K minus 1. It's AE Everybody good is here. I've just integrated, and because of that, the half will show up. That's all. So this is the cost of satisfying kth request, where FEK is the solution of the convex program. So what my optimality condition implies, if you remember, hopefully maybe you can backwards fit it, that why it makes sense to do it. So what was my optimality condition? That LE of summation FEI, I going from 1 through K, FEI is less than LE of the same thing. XEK. I'm just using this to get this. Okay. Now some elementary inequalities. Let 1, so alpha be something larger than 1, less than a beta, which is less than a 2. So alpha beta is some numbers between 1 and 2. Alpha times FEI, I going from 1 through capital K, minus beta XEI, I going from 1 through capital K. So once I square this is always greater than or equal to 0. And this also implies, just by opening the brackets, alpha square I equal to 1 to capital K, J equal to 1 to capital K, FEI, FEJ minus 2 alpha beta I equal to 1 to capital K, J equal to 1 to capital K, FEI, XEJ, and a plus beta square I've done nothing non-trivial. So this is number 5 and this is number 6. So look at 5. What am I trying to do? I am trying to put weights. So this is my, after capital K requests have arrived, essentially for each edge, this is the flow going through a particular edge, right? The summation. And this is for any other flow. So I'm weighting the flow which my algorithm is producing by a scalar multiple alpha and the flow generated by any other algorithm by beta. So this is the simplest starting point for comparing these two quantities. Right? See, for each edge, the latency function is the same. So if I can compare the amount of flow my algorithm is putting on top of it compared to any other flow, I should be able to compare them. Now directly I can't do it, so I will evaluate that with some quantity alpha and beta. It will clear, but essentially what will happen is we will make a choice for alpha and beta to claim our bound. So this is a very generic recipe if you want to compare your algorithm with respect to any other algorithm. That somehow try to find some succinct way of representing your cost, multiply that with some alpha, try to find a similar succinct way of writing the cost of any other algorithm, which includes the OPT, scale it up by beta, and take the square of the difference. And that happens to be greater than 0 trivially. And that gives you a starting point of these 1, 2, and 3 terms, which you can eventually compare again. So that is what we are going to do. So in this, from here onwards, will be lots of inequalities, which you will eventually forget what happened, but always remember where we started from. We are starting from this point, where we are trying to compare the flows assigned by an algorithm on a particular edge with respect to any other algorithm which is assigning XE of I. Okay. And eventually we'll make a choice for alpha and beta to claim what we want. So what do we want eventually? We want to say something like C algorithm is at most COPT times some function of the G of alpha beta. That's what eventually we will get. And then by choosing alpha and beta, we'll get the smallest such competitive ratio. That's what is going to happen using 5 and the optimality conditions. Because our algorithm, the only property we are using for our algorithm is that it is locally optimal. That given what we have seen already, we will be locally optimal. So another elementary relation, I going from 1 through capital K. Is this clear how to get this? These are equalities. So this is little k, and this is also little k. So now we'll use 7 for the first and second term of 6, which is here. So this has some product of this kind, xc times xcj. Similarly, this has a product of fei times fej. So that is what we want. What will we get? 2 times alpha square see, look at something, should keep observing what is happening. This is also in terms of my optimality condition. I just wrote this optimality condition in different language here. This was my optimality condition to begin with. This was written in terms of the summation of FEs plus BIs. So multiplied with FEs. So something like this is appearing here. It's not identical, but that's what we are headed towards. We eventually want to use the optimality condition. This is just rewriting. So that's the first term, minus 2 alpha beta. That is as before, no change. Is a cross term between FEI and XEJ plus the 2 beta square term, which is again little k equal to 1 to capital K, j equal to 1 to little k minus 1, XEJ plus half XEK times XEK. Okay, now multiply equation number A with the constant AE that defines our latency cost and add over all edges. Currently in 8 there is no summation across edges, it's only requests which are being added together. So this will give us summation, sorry, E belongs to E, AE and the whole thing, 2 alpha square. Yeah, this is too irritating to write, but there is no other way. The cross terms, and finally plus 2 beta square Okay, so far so good. So now if you recall, we chose 1 alpha beta to be less than 2. So this implies that 2 alpha square minus 2 alpha beta over k is how much? It's greater than equal to 2 alpha square minus alpha beta, which is greater than 0 for k greater than equal to 2. Everybody can verify this? Can I go ahead? So this must be number 9. And similarly, we can write 2 beta square minus 2 alpha beta to be greater than 2 beta square minus 2 beta square greater than equal to 0. Keep me honest, okay? I am prone to making mistakes in these sets of inequalities. So if something is not clear, shout. Okay, so now we'll multiply. This is multiply BE times FEK with 9 and BEXEK with 10. What do we get? Add them over all edges and all requests. So we get 2 alpha square minus alpha beta times BEFEK plus 2 beta square minus 2 alpha beta BEXEK summed over E in E and little k. And all this is greater than equal to 0 from 9 and 10. So just rewriting this tells us that E belongs to E. Two alpha square BEFEK. See, this is, so if you noticed, there are two terms to our cost, right? There is this quadratic type of term, and then there is this linear type of term. So for quadratic, we have essentially 5, because there are all these cross terms, FE times FE, XE times XE, and FE times XE. Now for the linear terms is what we are now handling. So for the linear terms, which is again taking something which is greater than 0 and multiplying them. So BEXE and BEFE are the linear terms. So that is what I am doing. So equation number 5 took care of the quadratic terms. Now I'm taking care of the linear terms. So minus 2 alpha beta BEXEK. Sorry, I told you to keep me honest. I already made a mistake. See, look, this is 2 alpha beta by k plus 2 beta square BEXEK minus 2 alpha beta over k summation. So this term here is coming from here. Other 3 terms are, one is here, this guy has gone here, and this guy has gone here. There are 4 terms above, 4 terms here, and all of this is still greater than equal to 0. Okay, so recall from our definition. What is the cost of assigning the kth request? Assigning kth request is C, or rather, let's look at the total cost. I don't want the kth request, I want the overall cost, because that is what I want to compare against OPT. So C capital K was C little k, K going from 1 to capital K, which was K equal to capital K, E in E. Hopefully you can at least remember this. It's very important that you remember this. F E I comes from 1 through K minus 1 plus half F E K plus B. Everybody remember this, right? Hopefully.
Yes.
Very good. So now try to identify. So let's call this number 11. So in 11 and did I not write this? Okay, let's call this 8A. So in 8A and 11, are they even visible? Try to find where is CK sitting, C capital K. Is it sitting somewhere? See, think of AE going inside. Okay, so AE times this part. What does it remind you of? This part.
It's the first term in CK.
Okay, now where should I find the second term? I will find the second term here. Where, remember, both are getting multiplied with 2 alpha square. So if I add 8A and 11, so adding 8A and 11, I can extract out 2 alpha square CK. And just to make sure that CK is with respect to my solution F, I will write CK square F. Now similarly for XC also, they're sitting here. With what multiplier? If you push AE here, this is also the first term for CK with respect to the flow X. If you want, you can put a under bar to represent the vector. And similarly, this guy here in 11. But that gets both of them are multiplied with 2 beta square. Are people with me? We have some extra terms, but at least CKF and CKX are common to, after I add 8 and 11, I can identify those. And the rest terms I will write here. So minus 2 alpha. I know this is way too overloaded, but at least try to see whatever beauty you can find. I will write it again, running out of space. So I've done no magic. I've just identified terms corresponding to CKF and CKX in 8A and 11 and written it in compact form. That's all I've done. And the two terms which remain are written as it is. So just to go back. So this part and this part was already part of my definition of C capital K. Similarly over here, this part and this part are already part of it. Now this 2 alpha beta as also a counterpart here to alpha beta. So that is what is written together as this part. And this last term over here is written as it is. So this is how I get up to here. Now I want to invoke the optimality of flow F, right? Because of the greedy algorithm. So which term I can found? Which term you think is in terms of that? See, these two terms cannot be touched. They're already in the form which I want to have. This is C capital KF, which is the cost of my algorithm. This is CK of X, which is cost of any other algorithm. What are the terms which I can invoke my optimality conditions? In other words, what are the terms which involve both F and X? There is only one term which involves both F and X, which is the middle term, which is minus 2 alpha beta summation So we did something earlier by invoking the optimality, wrote something up. What was that? That LE, if you remember, LE of summation FEI going from 1 through K times FEK was less than equal to LE of, do people remember this?
Summation FE, XEK.
So this we said from the optimality condition. Currently I have XEK. So what can I do with a negative sign? I can replace it with the FEK without changing this inequality. So this is my 12, 13 one. This is actually a recollection of the optimality condition. So using optimality condition in, let's call this 12, let's call this 12A. So using 12A into 12, what do I get? I can get rid of the XCK sitting here. Everything will be in terms of FEK. We can actually do more, so let's just do that. So 2 alpha beta E belongs to E, little k equal to capital K. I'm just writing this equation. Summation FEI K plus BE times XEK by 12A is greater than equal to 2 alpha beta belongs to E equal to 1 to capital K E summation FEI into FEK. Now I'm going to expand this further. 2 alpha beta E and K KE FEI I going from 1 to K minus 1 plus split it up into half FEK plus another half FEK. See here there are K terms. I'm writing K minus 1 here and taken the last one and split it up plus a BE and whole times FE. So this should be. And now once again invoking the definition of CKF, which is the total cost of the algorithm. Where is it? Yeah, this one. Total cost. We can write this as 2 alpha beta CK of F plus what is remains 2 alpha beta E K half FEK FEK. That's what it is. So using definition of CK we get here. Okay, so what have we done? So we were here. We had CKF on this side, CKX on this side. This annoying term which involved FE and XE, and this term which only involves FE. So we are not yet got rid of this. We are trying to write this again in terms of the CKF plus some FE times FE. So I'm just going to use that. So you get 2 alpha square, and this will now give rise to 2 alpha beta CKF because this is the minus sign. Minus alpha beta ke summation little k f e k f e k. The 2 and a 2 cancels. Plus 2 beta square ck of x and a minus 2 alpha beta over k be fe greater than. Okay, so now two terms you want to get rid of. One is this term and one is this term. Okay, what do you think we should do? Something very standard. In what form, if they show up, it will be useful for me. See, all I want to do is to get rid of this and this in terms of CKF, because then I'm in good shape. Because I have CKX, CKF here, which I can compare. I just don't know what these two terms look like, but I would like them to be in the form of CKF. So is there any way to do that? So tell me some inequality of the type. So what do I want? I want first an lower bound on this quantity. So what's the easiest lower bound you can tell me? Which is like universal. What kind of function is FEK whole square?
Convex function.
Yes. So what kind of inequalities do we know for convex functions? So let me know first that is this even true?
Yes, by Jensen's inequality.
We know it also in another name. Cauchy-Schwarz. It's also Cauchy-Schwarz. Okay, so suppose I use this. How do I get rid of these two annoying terms? This term, this one, and this one. I want to write it in terms of CKF. Now, if I use this inequality, so let me separate these good terms out. So the good terms are 2 alpha square minus 2 alpha beta CKF and plus 2 beta square CKX. So these terms I don't mind. Now I have this minus alpha beta. Using the Cauchy-Schwarz, I get summation AE 1 by K equal to 1 to capital K. If K whole square, this is over E, and minus 2 alpha beta by K summation. You should realize something suddenly has become similar. DEFEK. I have this. So if I bring this K out, I can always write this as K. So now look at the coefficient here and here. This one and this one only differ by a factor of 2. Now, can you just notice something about these last two terms? I want to write this as minus 2 alpha beta by K times something. What is that something? If you've been paying attention, you should be able to see.
CK of F.
CK of F, is that correct? Are you sure? How is it? So BEFEK is fine. Why is this first term the right thing? What was our CK of F? Go up. This was our CK of F, right? So why is that the correct thing? So when we open FEK whole square, what will happen? We'll get terms of the kind, the cross terms exactly like what we have here. So these are the cross terms which multiply FEI to FEIK. So what do we have now is FEK whole square. And when you open it up, we'll exactly get I going from something, J going from something, FEI and FEJ. So if you open it correctly, we'll in fact get CK of F. So after all this circus, what have I got? I have everything in terms of CKFs and CKCs. So what do I get by combining? So 2 alpha square minus 2 alpha beta minus another alpha beta by K times CK of F plus 2 beta square CK of X is greater than equal to 0. What should I do with this? Is it sufficient to claim what I wanted to do? So this tells me CK of F is how much compared to CK of X? 2 beta square divided by 2 alpha beta plus 2 alpha beta by K minus 2 alpha square. And remember what conditions I have always enforced for myself? This one. All right. So can you give me some numbers for which we can get our answer, which was 4k square over 1 plus k whole square. So there exist alpha beta values which can give me this answer. It's not difficult, but just takes a little bit of observation. This will do the trick. So if you choose alpha and beta to be these values, we'll exactly get this as CK of X. Now X is an arbitrary flow. So in particular, it could be the flow of the OPT, and we have what we wanted. Okay, so should we revisit what we did? There are lots of equations, but the bottom line was really two things. One was that we are solving a local convex program. So we effectively use the optimality conditions of that local program that compared to any other flow, given the current flow, which is up to k minus 1, the solution we are going to give is going to be better than the solution you're going to give me, any other solution which you're going to give me. But given the local solution, I have no comparison against the global solution. So that is the first important thing. And the second important concept, which I think is useful in a much larger setting, is this whole idea of starting with this kind of equation. So our decisions are impacting the flow passing through any edge over k request. Now, this is some other flow which we don't know of how much it is. Now, if we can try and compare it directly, it may not work. So what do? We choose arbitrary parameters alpha and beta. And we want to see that these two things are not very different. So by controlling alpha and beta, we're trying to essentially compare them at even pedestal. So hopefully there is some value of alpha and beta for which we will be able to compare these quantities. That's what essentially the big picture is. Now, once you write this, you get quadratic relations which we want. So which we wrote as how far did we get to? Yeah, we got to equation number 8a by just using that. So what did we do? We just started with 5. We opened it up. All right. And this was an elementary relation. This just to rewrite the summation as product of the summation or summation of the products in a particular form. And using that, we got our second order, which is either squares or cross products equation, which is 8a. the total cost of the algorithm had two parts. One was the cross terms or the square quadratic terms, another was the linear term. To take care of the linear terms, we had another two choices of these numbers where alpha and beta were between 1 and 2, so that these two were true, and we weighed them appropriately with the linear part of the cost function, BEFE and BEXE. And again, just rewriting, we got to 11. And then when we looked at 11 and 8a, which one took care of the quadratic term, other took care of the linear term, we identified some parts which are exactly capturing the cost of the algorithm, which is Ck of f, and cost of any other flow. And there were two remaining terms which are annoying. So this was one cross term which was annoying, and this was a linear term which was less annoying. CKF and CKX were easily identified, so those are not the problem. And now for this was the only place where we actually use the optimality condition. That at optimality, because FE being optimal, there is some relationship between, so 12a is that relationship that the latency function evaluated at the sum flow times the flow on that edge is going to be less than latency evaluated at the sum of the flow times XC for any other flow. So this essentially gave us a handle on how do you take care of one term, which was the cross term. And once we wrote that, this is just a rewriting of that. So this is rewriting. This is just directly from the optimality. And this is just using the definition of CKF. So what did we do? We also did take care of the third term in terms of one CKF and one extra product term, which involved the identical terms, FEK times FEK. So rather than having, so earlier we had lots of annoying terms here, which are products of XEK and FEK. We ended up only product of FE times FE. Then we use Cauchy-Schwarz. And again, the guess to make here is because this is 2 alpha beta by k, we would like this also to be alpha beta by k so that we can combine these two terms. And one way to do that was to use Cauchy-Schwarz to get in terms of 1 by k. So now I can combine these two coefficients, alpha beta by k and 2 alpha beta by k. They only differ by 2 times. And my objective function or the total cost of the function already had 1 by 2 in one of the terms. So that asymmetry was already there. And exploiting that, I was able to write the final two annoying terms as 2 times alpha beta by k times Ck of f. So that's the big picture result. Very elementary, but very powerful. Any questions? I know this is like long set of inequalities, but still if you catch as much as you can, because if I give you a new algorithm to work with, what would you do? You would try to somehow compare what your greedy algorithm is doing compared to what any other algorithm would do. And if you can get handle of that, that is one particular way of doing this is what was illustrated today.